Good morning, everybody, and welcome for another fantastic edition of Mr. Neuberts amazing video lesson, part 14 now. Today we're going to talk about Newton's second law, but I want to review a little bit yesterday from yesterday's demonstrations of the bowling ball down the driveway and the baseball down the driveway, demonstrating Newton's first law of motion. Objects at rest remain at rest unless acted upon by an unbalanced force. So anything that's stationary wants to stay there. Objects in motion will remain in motion at a constant speed or velocity in a straight line unless acted upon by an unbalanced force. So if I throw a ball in space, there's no air resistance, there's very little gravity, you're in the middle of between the moon and Earth, it's going to go in a straight line. Because there's no unbalanced force except a little bit of gravity affecting its motion. It's about the best example of Newton's first law you can get, moving in a straight line at a constant velocity. Some examples from the real world that might affect you. You guys are going to be driving in a few years. Scary as that seems. So you're sitting in a traffic light. There's a big semi-truck next to you, and you're at the traffic light. It's a red light. Which one's going to be able to accelerate easier when the light turns green? Your car will. Obviously, it has less mass, and therefore, Newton would say it has less inertia. Inertia is a tendency of an object to resist a change in motion. So the larger the object, the more mass it has, the more inertia it has. In the same context, which vehicle, the semi-truck or your little car, is going to be able to stop in case somebody pulls out in front of you? Which one's going to be able to stop quicker? Your car, because it has less mass and therefore it has less inertia. The semi-truck has more inertia, has a tendency to keep going because it's so massive, 30,000 pounds of bananas or something it's carrying. So it's not going to be able to slow down and stop easily. As a new driver, you've got to keep this in mind. You're out with friends, you're at McDonald's or something, you pull out onto Market Street without looking carefully to the left. You didn't notice that semi-truck was blown through the light by Taco Bell and is barreling down on you because it has a lot of inertia. You pull out too soon and he can't stop, and you're going to get T-boned. That's a T-bone right there. You're going to get T-boned on your side, and you might not like the outcome of that one, okay, to put it nicely. Give yourself plenty of room before you pull out, because cars, trucks, especially big semi-trucks, have a lot of inertia. They can't stop quickly, okay? Something else that has to do with this first law, objects in motion remain in motion. You're driving down the road. You didn't put your seatbelt on. And let's say you don't have a car with an airbag, so you're driving down the road. You swerve to avoid a deer. You don't want to hit the pretty little deer. So you swerve, you lose control, you hit a tree. The car stops almost immediately. You're unbelted. What happens to you? Objects in motion remain in motion. Let's say you're doing 40 miles an hour down Bath Road. You avoid a deer, you slam into a tree. The car stops quickly, you keep going. Okay? You have a lot of inertia, you're in motion at 40 miles an hour. How fast are you going when your pretty little face hits the windshield? About 40 miles an hour, okay? Wear your seatbelt, okay? Wear your seatbelts every time you drive, and don't pull out in front of semis, okay? Because they have a lot of inertia, they can't stop quick. Okay, second law is a formula. We're not going to do much math in here, hardly at all. I think there's one problem on the review sheet, the math problem. It's easy. If you look in your book on page 53, it's a simple formula. In fact, here it is. Let me put it on the magic screen. There's the magic screen. There's Newton. All right, you ready? The more force a moving object, the more object will accelerate. When a force moves two different masses, the lighter mass will accelerate more than the heavier mass. By increasing the force, acceleration increases. By increasing the mass, acceleration decreases. You got all that? Just kidding. Let's slow it down. What David was looking at is three different variables: force, mass, and I don't know if that's going to pop up on the screen, but something came up on the screen. force equals mass times acceleration. Okay? Force, we know, is measured in newtons, capital N. Mass is going to be measured in kilograms, kg, and acceleration is going to be in meters per second per second. In the book they say meters per second squared. Okay? And it's simply multiplying mass of the object times the acceleration will give the amount of force in newtons. Okay? In the book, we have an example of a water skier. And they're calculating the amount of force. Okay? 55 kilograms times 2 meters per second squared gives you 110 newtons. That's how much force was applied. Okay? So there's one problem on the review. We just simply multiply mass times acceleration. We're not going to get into math. I'd rather be in class with you in person to teach you the math end of this. In more practical terms, looking at the second law, okay, you can flip-flop, you can flip around the, if I can get this. There we kind of go. You can flip the letters in your formulas and look at acceleration, how acceleration equals force over mass. So if the acceleration can depend on the mass, or the amount of acceleration can depend on the amount of force. Okay, this kid's pushing a shopping cart that's empty. He's going to have a lot of acceleration. Okay, if we keep the force the same, okay, and add mass, you can see it's full now. You're adding mass, so if mass goes up, acceleration is going to go down. Okay. If force stays the same, he's pushing with the same amount of force. Okay, they don't have a vector arrow; they have vector arrows for acceleration. But if force stays the same, he's pushing the same amount of force with an empty cart as a full cart. The acceleration is going to be less because there's more mass. Okay, mass goes up, acceleration goes down. If force stays the same. In this case, he's applying more force. Okay, the mass hasn't changed from this one to this one. It's the amount of force. You can see by his body position, he's applying more force to it. Okay, so if force, in this case, if force goes up and mass stays the same, then acceleration is going to increase. Okay? So it's just looking at those relationships. Pretty easy part of his law. Just looking at it statistically, the relationship between force, mass, and acceleration. Okay. So not too much to do today. Watch this little video. There's a cool video that demonstrates this idea from the space station. That's kind of neat because it's in microgravity and things are kind of floating around, and you don't have too much air resistance to worry about. You're inside the station, which has air, but that's negligible. Okay, and then tomorrow, if you do want to read ahead, you can read on to the Newton's third law. If you want to read on that tonight, and I'll have the guided reading and study posted. But for right now, just you're watching my video. Watch the space station video, and then do the review. Any old homework, continue to submit it so I can get it graded and get it in the grade book for you. And that's it. Have a good day. Should be nicer today, warmer out. And bye-bye.